yeah, the last one blew up. All right, so here we go. So today, hopefully, like I say, we'll finish this up. This will be our last chunk of notes. So basically, we're going to be expanding on what we've done the last 2 days. We got to kind of finish our simple harmonic motion. All right. So all of the examples that we looked at the other day were very sort of simple motion, right, where the object was moving along a nice straight line. All of the examples that we specifically talked about were springs, but they didn't necessarily have to be springs. The important thing was that whatever our restoring force was proportional to the amount that it was displaced. Yes? All right. So we're going to kind of pick up there today, but look at some slightly more complicated examples of simple harmonic motion. Honestly, basically, what it's going to amount to is just replacing some linear values with angular values. Okay? So honestly, this should not be that big of a deal. All right? So first of all, the first thing we need to learn about is what's called a torsion pendulum. All right? So a regular pendulum is...
What?
Lights in the background. Okay, so a regular pendulum, obviously, is this. And we learned last year that the period of a simple pendulum was 2 pi times the square root of L over G. All right, and we'll come back to that in a minute. All right, so a regular pendulum looks like this. It swings back and forth, following, again, simple harmonic motion. All right. But what causes it to swing is gravity and torque produced by gravity. We'll get to all this. All right. So a torsion pendulum is slightly different, and frustratingly, none of the science education companies make a great one. So this is one that I found here from one of Mr. Runner's students. All right, so you could make this into just a regular oscillating spring system, right? Like if I pull this down, then it oscillates up and down, and then it becomes what we talked about yesterday, right? But if instead of stretching it, if I torque it, in other words, if I twist it a little bit, then it becomes a torsion pendulum. So if you ignore the bounce, I couldn't do it without bouncing it. And you see how it's twisting back and forth like this? Okay? So that twisting motion creates, or is an example of what's called a torsion pendulum. Follow? All right? And so it turns out that in the same way that for a spring that's stretched linearly, the force is proportional to the linear displacement, it turns out that for a... Oh, here, the bars are on this side now. It turns out that for a torsion pendulum, the torque produced is, instead of being k times x, it's kappa times theta. Okay? So long story short, instead of the force being proportional to the displacement, the torque is proportional to the angular displacement. Okay? Peter?
Is torsion a mixture of torque and tension?
Yes. That's exactly what it is. Yes. Because tension, you're making things tighter, right? When you twist something, you can be, tightening it. Yeah.
Is K the same?
So, K is not the same. So, that was going to be the next thing I was going to talk about. So,
I'll just ask. Just leave it be.
all right. So first of all, let's talk about letters, because this chapter, the notation in this chapter flat out just sucks. All right? And there's no getting around it. So there are 3 different things that are K. So let me talk about how I'm going to draw my letters. I would encourage you to do the same so that you don't get mixed up between what your letters are. All right? So K, that's a capital K, as in kinetic energy. All right? The spring constant. The spring constant, I use a lowercase cursive k. All right? And this guy here is the Greek letter kappa. All right? And I'm going to draw it like this. So it's like a fish with a line through it. It's a K, but I'm just drawing a little loop where the K meets the line. You know what I mean, right? Clear?
Yes.
All right. So, well, perfect thing to happen in gross point too, right?
Okay.
Okay. So everybody good with that? All right. Now, our regular spring constant is in units of newtons per meter, right? If you divide both sides by x, you get the force divided by the displacement, the number of newtons per meter, right? Okay. Our new one, this kappa, is a torsional spring constant. So that's how we'll refer to that, torsional spring constant. Okay? And it's going to be equal to, what are the units going to be? So torque is in Newton meters per radian. Right? It's how much torque is produced per unit of angular displacement. Follow? All right, so all of that's really intimidating and like, but honestly, if you just sort of in your head just think of, you know, torque being analogous to force, the spring constants being analogous, and displacements being analogous, you're literally just, everything else is the same. Okay? So, yeah, Patrick. I can't hear you because you're talking in your hand. Right, so the idea is if I twist it a little bit, at that point the spring is pulling back with some amount of torque.
Oh.
Does that make sense? Like the more you twist the spring, the tighter it gets, and so the more torque it's going to produce trying to twist it back. Follow?
It's not right there.
Everybody good with that? Okay, so any problems with what we just talked about here? All right, so once you've got your torsional pendulum, it turns out that the motion that this exhibits is basically the same as, if I could do it without making it bounce, it's basically the same as the motion that this exhibits. I need to build a new one. Okay? So that motion, in terms of angular position, follows the same rules that this makes in terms of linear position. Cool? All right, so here's where things get stupid. Remember yesterday, or I guess it would have been, what, Tuesday? I commented that omega is angular frequency, not angular velocity.
Now it is.
It's a back angular velocity.
Well, I don't know who chose this notation, but this is another time where if I had a time machine, I'd go punch somebody. So since we've already designated omega, instead of calling it angular velocity like we have all year, right? This is our angular frequency. Now we need to come up with a new name for angular velocity.
Yeah.
All right? So we're going to use capital letter omega to mean angular velocity.
So tell me why they didn't just make omega angular.
And why they didn't make the other omega capital omega and leave lowercase omega as it was, I don't know. Like I said, time machine. All right?
Wait.
So I lost a whole bunch of you. Let me rewind.
No, I
Let me rewind. So this is. So remember, yes, the other day we learned the equation for position at time t, right? Okay, and it was maximum position times the cosine of omega t plus phi, right? So this is the same thing, except we replace maximum linear position with maximum angular position. Otherwise, it's exactly the same, right? Good? So once we had that x equation, how did we find the velocity? Just took a derivative. So this is the exact same thing. So if I take the derivative of this, it gives me angular velocity. All right? The problem is I can't just call it lowercase omega because some dumb-head picked omega to be angular frequency here. Okay? Follow? So what the book does to alleviate that confusion is the book just calls it d theta dt. So if you prefer that instead of using the capital omega, great. Okay? just make sure that you understand that this omega here does not represent the angular velocity of the thing at a given instant. It's the angular frequency. All right? I know. I like I say, I hate that this is the way the notation is done. But I don't want to mess with it too much because when you're taking the AP test, the graders need to know what your notation means. You know what I mean?
That's so
Unless
confusing.
you like right at the top.
Unless you, yeah.
Wait, so like which one is accepted? Both are like angular frequency and angular velocity in different contexts?
Yeah. So
So,
the only time that this will be an issue is if you're talking about angular simple harmonic motion. All right? Honestly, if it came up on the test anywhere other than a multiple choice, I'd be really surprised. Okay? But I can't promise.
we call this
All right?
the
So,
LPC stem.
yeah, I may have just jinxed us.
Oh,
Okay,
remember all
so
that stuff?
here's our angular
All the space
position.
and stuff?
Take the derivative of it, and it gives our angular velocity. Take the derivative of that, and it gives our angular acceleration. Cool? All right? Multiplying both sides by rotational inertia, right? Because torque is I alpha. Tells us that the torque at a given time is this. And notice that in the same way as before, our force was proportional to our displacement. Now, our torque is proportional to our angular displacement. Follow? Because I and omega is our constant. Follow or no? As much as you can, I guess. Some of this will just be like you got to dig in and try it. Okay?
So is that like the I omega? Is that omega the angular frequency still?
For this chapter, you guys, that lowercase letter omega will always mean angular frequency. Let me say that again. If I didn't make this clear before, lowercase omega for this whole chapter means angular frequency, without exception. If I write lowercase omega on the board, I mean angular frequency. Clear? If I want angular velocity, I'll either write d theta dt or I'll use this stupid capital, and I'll call attention to it so you don't get confused. Fair? All right. Very good, very good. Okay, any problems? Did I lose anybody there? Too much, like beyond the point of return? We good? Okay. All right, so notice what I just did here is I said, oh, well, this is my constant, right? Just like yesterday we had, what was it, m omega squared was our constant. Now our constant is I omega squared, right? Linear inertia becomes rotational inertia. Cool? All right, and then in the same way that we have F equals kx, now we have torque equals kappa theta.
Sounds like we're about to enter.
All right, problems? All right, I believe the next page has an example, I hope. Aha, yes. All right, so this example is actually fairly kind of straightforward, and I gave you this hint that you don't even need to use to solve it. Basically, the main thing that I want to show you in the course of this example is that once we get to a certain point, it's going to be the exact same as the example we did yesterday, except everything's angular instead of linear. All right? So, a torsion pendulum consists of a metal disc with a wire running through its center. So this is sort of like the classic thing. So picture a metal disc with a wire. You twist it, and it's going to like kind of oscillate, you know, back and forth, like that. Cool? So that's what this description means. A metal disc with a wire running through its center, and it's soldered into place. The wire is mounted vertically on clamps and pulled taut. Figure A gives a magnitude torque of the torque needed to rotate the disc about the center and thus twist the wire versus the rotation angle. The vertical axis is set by 4 times 10 to the negative third newtons per meter. 4 times 10 to the negative third newton meters. Sorry, I think I said newtons per meter. Okay, so that's the top of the graph. The disc is rotated to an angle of 0.2 radians and then released. Figure B shows the resulting oscillation. So this is our position time graph, right? It's just theta instead of x. Good? All right, so very, very similar to what we did yesterday. So let's see. Let's write down what we know. Well, I guess maybe even before we do that, what can I do with that graph? Does anybody see what the purpose of that graph is? What do you got, Christine? Find kappa, right? This is showing me that the torque provided by the spring is proportional to the theta, right? And we know torque is kappa theta. So find the slope of that line, right? Or even more simply, at this point, what I know is that, here, let me put a star there so we know what's going on. All right, so at that point, what we know is the torque provided is 4 times 10 to the negative third Newton meters. We know that our displacement is 0.20 radians. And we know that torque is negative kappa theta, right? And solve for kappa. So if you divide it out, you can do 0.02 Newton meters per radian. Let me pause there for a minuto. Are there questiones?
I don't think I'm ever going to be able to write an A right.
I know.
Yeah.
So we still have another test right now, is it?
Next Friday is the goal. And that gives us 2 weeks to do practice stuff for the AP test.
Yes, we know. Is this,
Tentatively test on this stuff next Friday.
is the AP test for this on the first week or the second week?
It's the second Monday. Okay, everybody good up to there? All right, now, question A says, what is the rotational inertia of the disk, right? So let's go back at the previous page where we've got our equations and find an equation that has rotational inertia in it. None of this garbage does. Oh, aha! Ha 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 ha! Aha! Oh, what the bleep? Man. That was weird. I'm going to try that again. Ha 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 ha! Hooray! Okay, it worked that time. Okay, so, So if kappa is I omega squared and I'm trying to find I, we just found kappa. What's the other thing I need to know? Omega. What's the definition of omega? Angular frequency, right? So we learned yesterday that the angular frequency is 2 pi over the period, right? Good? So what's the period of our graph, you guys? 0.04 seconds. Oh, it's... oh, you're right, just 0.4, my bad. Thank you. Thank you, Justin. Do you like your new desk, by the way? Uh-huh. Don't do that. I just moved. It takes me time to haul the desks back. I don't have room. All right. Is everybody good? All right. So if you solve this, you get, is it 15.7?
Yeah.
Radians per second. And so now I can find my rotational inertia, right? Pink and the orange are too close together. I don't like them. You need to change
I didn't even realize those were different colors until you said it.
Oh.
Nothing's obvious.
Would you lose about? Stop! If you guys are confused, you gotta stop me.
Super quick equation for W.
So it's definition. So the idea is, remember, angular frequency. You sure?
Yep. 100%.
Is everybody okay with how I got that angular frequency? The 2 pi over t?
Yeah.
Okay, stop me when I lose you guys. I get it. Like, this is. All
Well, it's the last statement. That's not fair.
right, everybody good? All right. So that means that I is kappa over omega squared. Solve for it. and you get the answer that was on the sheet. What is it? 8.11 times 10 to the negative fifth kilogram meters squared. Cool?
Which K is that? Oh, kilogram.
Yeah, that's a kilograms, yeah. Daniel. Shh. I don't know. I'd have to sit and figure it out. Say it one more time. Let me finish the notes and then I'll look at it, okay? All right. Okay, these are pretty good. Okay. Okay, so then B wants to know the maximum angular speed. The maximum angular speed. So to be clear, and it says it here in the problem. It says, caution, don't confuse the constant angular frequency with the changing angular speed, right? Remember, your angular frequency is constant because the rate at which your thing bounces back and forth has a fixed period, right? Similarly, this guy, theoretically, once it's going, it should oscillate with a constant frequency. All right? But what's changing is how fast the little points are moving.
Yeah.
Because they stop and they
exactly.
switch directions.
Does that make sense, you guys? Very well said. Okay, so so the hint, actually, I should have deleted it. There's a way easier way to do it that does not use the hint. Does anybody see an easy way to find the maximum angular velocity? I will sign Sarah's pass. What do you think?
Take the derivative.
Yeah, it's a maximum.
What do you got, Maggie? Guys?
It's just the angular frequency times the maximum.
Good. It's just the angular frequency times the maximum theta. How'd you figure that out?
Oh, yeah.
How'd you figure that out?
Because I just know it from the linear book.
Yeah. Look, you guys. This is a lot of work for me to get to a stupid highlighter. Because look, isn't this going to be... Oh, fail. Isn't that going to be our maximum angular velocity?
Yeah.
Right? Because sine oscillates between 1 and negative 1. So we want to maximize it, put it at 1. So that means omega times theta max. Right? Just like yesterday, we learned that the maximum velocity was omega times x max, which I think is what Maggie meant when she said, I just knew it.
Maximum angular speed.
So,
velocity is capital omega.
So
that mass equals negative w squared.
Is it square?
So what did we just decide? It was omega times theta max, right? Shh. So omega we know to be 15.7 radians per second. Our theta max was, is it 0.02? Yes. Is that right, you guys? Help me out. Oh no, it's 0.2. All right, and you get 3.14.
Wait.
Wait. How does this work? I don't remember. Let's not get bogged down with it. It's supposed to be radians per second. Oh, this is, no, that wouldn't even work either. Shoot. There's got to be a radians per radian in there somewhere. That's really frustrating. I don't know.
It just works.
It just works.
Yeah, it might be
It just does.
All right. Everybody good? All right. So that's the deal. Problems with any of that? Okay. So now that's torsion pendulums. So now we need to talk about simple pendulums and physical pendulums. All right. We've kind of done the hard part of this. Okay. So any questions before I go on to the other stuff? Okay. All right. Now, before we go any further, we have to make use of a math property that is often used in math. That was the worst sentence ever said by anybody. So it turns out that for theta in radians, as opposed to degrees or something, it turns out that it's supposed to say 4. And for small values of theta, that was really funny. It turns out that the sine of an angle
Oh my god, equals the angle?
equals the angle.
Jen, did we just do this? Oh, I hate this.
All right, so grab a calculator, you guys, and find the sine. Put your calculator in degrees. I'm sorry, put your calculator in radians, and find the sine of like 0.1 radian. Okay, that's about the same. That's about the same as 5 degrees ish. So find the sine of 0.1 radians. It's basically 0.1, right? Okay. Do sine of 0.2. Do the sine of 0.2. It's like 0.199 something, right? So it turns out that if you have small values of theta, it turns out that the sine of theta is approximately equal to theta in radians. All right? All right, now, the proof that I'm about to do, I have seen on an old AP test. This is a thing you need to know how to do. On that last test, some of you guys really struggled with those derivations, even though they were on the 2 FRQs that I gave you. You need to know how to do these derivations when I say you need to do these, okay? So, here is such a case. All right, what we are going to do right now is we are going to derive this equation that we learned last year. All right? All right? So we can do it 2 different ways. You can do it by considering. So if I take this pendulum and pull it back, that's my pivot point, right? It has to be because it's pivoting around that point up there, right? Good. And my force is vertical, right? Do you guys agree that there's a torque being placed on this rope pendulum thing that's causing it to rotate, right? Okay? So one way that we can come up with this equation is by thinking of this in terms of the torque restoring the pendulum back to its initial position. Okay? In other words, using what we just learned. Okay? So if you do that, here's what you get. No, I like this better. Ooh. Okay, so if I want to calculate the torque here, remember, torque is going to be, well, so name the force that provides, what's the name of the force that restores the pendulum back to its starting spot? Gravity, right? So I want the torque from gravity, right? So the torque from gravity should be, well, let's see. Torque is force times, so let's call L the length of the pendulum. So wouldn't that be the length of my lever arm also? Times the sine of the angle between those 2 vectors. So let me highlight some stuff here. So here is my lever arm, right? That's my lever arm. Here is my force. So the angle that I actually want is this big guy here. Follow? Okay. Everybody following or no?
Yeah.
Could you use the small angle?
Okay, but you can use the small angle because it turns out that the sine of supplementary angles are equal. Okay, in other words, the sine of theta and the sine of 180 minus theta is the same thing. So what that means is this theta here is the same as this theta here. So we just want sine of theta. Good? So as long as I pull this back a small angle measured in radians, then sine of theta is just theta, right?
So does that mean
I know, I don't like it either. It makes my skin crawl a little bit. It only works for small angles.
so like
Yeah, what's our definition of a small angle?
The smaller it is, the closer it is.
Yeah, but like, where's the line?
It will not be an issue. It won't be an issue.
what if someone like
All right.
wrote a mail on that?
If you've got if you've got a simple pendulum like this is called a simple pendulum, you can always assume that it's a small angle. Yes. Pam? Okay. All right. So, all right. So, well, then I can call this guy. Do you guys agree that the force of gravity is going to be constant?
Yes.
Right? The length of the pendulum is constant. So now I've got that my restoring torque is kappa times theta.
What? That's just a random kappa again?
No, it's the same kappa.
Oh.
It's, right? Because we just learned that for a torsion pendulum, the torque is proportional to the theta, right? Same thing is true here. The torque that restores the pendulum back is proportional to the theta. Cool? All right? So now we just go, and we learned a minute ago that torque was 2 pi times the square root of I over kappa, right? Oh, my kappa doesn't look like a kappa.
Every time you pull out those brackets, I'm reassured of my assumptions right now.
Sorry?
Sorry, talk about
You guys, does that make sense? Oh, shoot, that is period. Thank you. Holy cow. Thank you, Christine. Here, let me do this in.
Wait, what? There's different T's?
It's the same.
No, there's torque and there's period.
Oh, it's working here. Yeah.
I know. I'm sorry, guys. Thank you, Christine. Good save. Yep, it's just that last one. And so, what's wrong, Patrick?
Patrick's just a big dummy.
Are you the one that did this omega thing? Never mind. Okay. All right. So is everybody good? All right. So now I'm just going to substitute. Look, we know that kappa is FGL. So let's see. Kappa is
It's cookie day.
Fg times L. That's the same as mass times gravity times L, right? All right. Now, what's the rotational inertia of that? It's a point particle, right? This mass is very small. I'm sorry, the size of that mass is very small compared to the radius, right? So it's mr squared, but what's r?
L squared something.
Cool. So let's plug in our numbers. So you get, let's see, I is ml squared. Nope, 2 pi times the square root of, and then kappa is mgl. Why am I happy? Because the m's cancel. One of the l's cancel. Oops. And you're left with the equation at the top of the page there. So I'm going to draw a smiley face, and then I'm going to answer Adam's question.
So I see how we derived the equation of the but did we just assume we already knew this first?
I
This,
was gonna ask that too.
yep, so I'm glad you guys picked up on this. So yes, this we proved over here.
What?
All right. So okay. So I guess I did do a little bit of hand waving. Do you guys remember that 2 days ago we proved this, right? By substituting, we said, oh, well, we know omega is 2 pi over t, we know k is m omega squared, and we did some substituting and got this. All right, the algebra here is literally the exact same as the algebra on how to get this.
Can you go back?
So do we have to worry about how we...
Proving that? No.
Can you go back to the first
Oh no, we're not going to finish. We're not going to quite finish.
I have a question, but I'm scared to ask you now.
No, go ahead. Ask. It doesn't make sense to move on if you guys are confused. So.
You canceled the battle, but... Oh, wait.
So it was.
Okay. No, I'm good now.
You're good?
Yeah. Yeah.
So it was ml squared over mgl. So if I lost you
L
there,
over G.
I canceled the L and I canceled the squared.
Yeah, I accidentally didn't have an M, and then one of the M's disappeared, and I was like confused.
All right, we're almost done. You guys, Dana? What do you got?
So anytime we have an equation that's t equals 2 pi, are they all period, or is one of them torque? And
All of the t equals 2 pi something or period.
okay. And the okay.
Good?
Yeah.
I know. I'm sorry.
No, it's cool. The first one is square root of k over g.
M over. Wait, no, L over G.
L over G.
Oh,
Or
okay. So
I
there's
over
only
K.
two. There's not three different.
All right. So let's summarize this real quick, you guys. So as of right now, we've learned 3 different period equations.
L over K is...
We've got
There's just like extra letters there that you canceled the L over G. I can't even say it right. Don't listen to me. I don't know what I'm
I think you switched them here.
Yeah, there's just like extra variables that you can't say one or the other.
Okay.
Okay, we've got angular force,
What?
like torsion.
Yeah, I'm just confused on where you get the M over K.
That's the old one.
We proved that on.
Oh.
So, but notice these two equations are essentially the same thing, right?
Yeah,
Like, what's mass is a measure of inertia, right?
yeah.
So m and I are counterparts, and k and kappa are counterparts. All right. So those can be assumed to be true because that's a direct result of the definition of simple harmonic motion. Okay? From there, using wizardry, we can derive the pendulum one that I just gave you. So this puts it all in one spot. So the period of a pendulum is 2 pi root L over G, which is not at all obvious, but true. Good?
What's L?
L is the length of the pendulum. Good?
And G is the force of gravity.
G is acceleration of gravity.
Yeah.
Everybody good?
Yeah. And we proved that with the others.
Yes.
It's a banana.
All right, are we good? All right. So I think the math in that, so we just sort of derived this, right? Using torsion, using the restoring torque, right? I think that mathematically this way is easier. It's like less steps, right? Because all we did was we replaced sine theta with theta, and then we made our constant FGL, right? Doing it using the restoring force gives you the same result. I think conceptually it's easier, but the math is one step harder.
How many equations can I put in my calculator?
You know what? I think we muscle through. We're almost. All right. So here's the other way to do it, considering the restoring force. All right. So look, you guys. is, when I let this thing go, it's going to swing like this, right?
Yeah.
The force that's pulling it back towards the center is not all of gravity, right? Here's my force of gravity. What I really care about is the component of gravity that goes that way, right? So what do we want to call that? FG?
That way.
That way? I'm going to call it parallel because it's parallel to the motion. Or should we call it perpendicular because it's perpendicular to the rope?
Oh,
Perpendicular.
How about
How about mg sine theta?
FG sine. Wow, Dad, just say my.
I'm going to do this. FG that way.
Yes, that way.
Whatever, it doesn't really matter.
That way.
All right? And this is FG that way. How about that?
I made it. It's really
Cool? All right? So, do you guys agree that it's this FG that way that's going to restore the pendulum back to its starting position?
Yes.
All right? And do you guys agree that this theta up here is the same as this theta here? Ah, so that means that the opposite side must be FG sine theta, right? Okay? So my restoring force is Fg that way, which is the same as Fg sine theta, which for small angles is the same as Fg theta.
So we can only do that in this chapter, right?
Yes, that's the only thing you can do this chapter. Like this is the only, all year, the only time you can do that. Good? All right, now we can use a jumper. Theta is the same as x over L, where x is how far I pulled it back. Oh, cool. Now my force is proportional to the displacement. Yes.
So that x is just the horizontal component, right?
It's actually not. It's the arc length. But for small angles, they're pretty much the same thing. Follow? All right, so if Fg that way is Fg over L times x, that's the same as mg over L times x. What am I going to do? Oh, sorry guys. Are we good? All right, so what am I going to do now, you guys? One last step.
Oh man.
Call this mess here K. Oh, no, hold on. K. Right? Because now we're talking about a linear force and the corresponding linear constant. Yes. So lowercase spring constant K. So we can think of it as a spring constant. It's not technically a spring, but it behaves like a spring. Follow?
Do we need a negative in there somewhere?
Yeah. All right. So remember, we learned before that period is 2 pi root m over k.
Yes.
K is that mess.
The ends cancel. Yay.
The m's cancel, and you get 2 pi root L over G.
Whoa. I recognize that.
Good, because that's what we're. I mean, like that sounded snarky. I'm sorry, but that was the point.
No.
Sorry, I'm an
That was the
asshole.
point of my statement as well.
Oh, good.
Yeah.
All right, are we good, you guys? All right, we've only got 3 minutes, so we unfortunately are going to have to finish up. I guess.
Go through. We got this. Let's go.
How many doing a muscle through?
Yes.
That's not enough. All right. Okay. It's not bad. It's like 10 minutes. Like, I think a legit 10 minutes. Me knowing that I talk too much, and I think it's 10 minutes. So, hey guys, real quick, I will remind you of the caution that I gave you guys the other day. So 15.1 is due on Monday. 15.2 is due on Wednesday. We'll have to finish up the last chunk of the notes, I guess, Monday before we go over 15.1. So try to get as much of the chapter 15 stuff done over the weekend as you can. And then just so you guys know, tentatively, here's how I'm thinking about using the next 2 weeks. We need to get some practice in with like real AP FRQs and real AP multiple choice sections, right? They're 45 minutes each. So what I'm thinking is your homework each night will be either an FRQ or a multiple choice section. Make sense? So either a, yes. And you should time yourselves and do the best you can. At the beginning, I might say give yourself an hour, and then as you get, the first week give yourself an hour, second week scale down to 45 minutes. Something like that.